I'm going to just have a short walkthrough of my progress integrating Stwo to Powdr. As Powdr is a tool to define ZKVM. Now we have a RISC-V VM, and you can choose to use different approvers to generate the proof for your ZKVM. And then what this means is kind of we create the polynomial constraint for the ZKVM independent of the prover we are using. That's allow you to choose different provers. And then this polynomial constraint now is more looks like error constraint. We don't have R1CS. We do have a hello2 as a snark, but that's how we transfer polynomial looks like error to hello2 constraint. Now I'm going to transfer this polynomial constraint to Stwo. To use a prover to generate a proof, you basically you need two things. You need your polynomial constraint and then the witness. For the polynomial constraint, it's basically how you write your circuit. In Powdr, when it generates the polynomials, it's a really fundamental, like a polynomial, you see a lot of equations. And then, but in Stwo, what I need to do is to transfer these polynomials to Stwo's constraint. I use their API to present these polynomials. When we have in Powdr, when we think about we want to integrate a new prover, we have some interface that I need to define to kind of connect the Powdr to the backend prover. Here, this is Rust code. What you firstly look at is you need to kind of make a new prover available. We have a backend type trait that basically specify how many provers we support. And then the first thing I need to do is I'm going to make my Stwo available here in this backend type. This allows the user, when you use Powdr, you can choose directly what type of prover you want to use. And then there will be another tool interface trait. This is about Rust. Backend factory where you can initialize your prover. And the backend where you have the most important function, the proof and the verify. And then there will be some other functions to set up verification key if you need and something like that. So now I kind of define this trait for my Stwo prover, and I can show you kind of roughly progress how the proof process in Powdr works now. In this prover, when this proof function, when you come into the proof function, now it's basically what I'm doing is to try to prove the polynomials and witness generated from the Powdr VM. We need to set up this quite a typical stack process. You need to set up your blow up factor, and power proof of work bits, and to make your security level satisfied. And then the next step is these twiddles. I didn't see these twiddles in other projects because here they write it specifically, and you set this up, and then afterwards you use it a lot in FFT. But I don't think it's can be seen as a typical step. And then this next step generates Stwo circuit trees. This is where I transfer the polynomial generated from Powdr to the circuit that can be accepted by Stwo. And then the next following steps all come from Stwo. You use it to generate proof. They have this. I think I will go to different path. let's to check about the circuit builder. Here, the k function here is these two Stwo expression. What it does is get a lot of polynomial from Powdr and transfer some simple expressions, and then I use these simple expressions to put them into Stwo prover. The long polynomial we can see, but it can be very long, but you can always decompose it, a polynomial into left hand and right hand. And then we do this recursively to make very simple expressions. This is how in Powdr I do the decomposition. Then I can talk about little about Stwo, how you write a circuit in Stwo. In Stwo, if you want to write a circuit, the thing you need to check first is how they define their circuit. They have two backend. They call it backend, which means basically two different constraint framework you can use to define your circuit. The CPU backend is very similar to what we know from other provers, Plonky 3 based on Stark, but the SMD backend is more powerful. It allows you to do parallel computation, so it's more optimized. So I would say if you want the best result, you should always look at the SIMD backend. And then what you need to do next is you need to check this trait they defined. You create a struct for your own circuit and then apply this trait framework evaluation to your struct and define the circuit here. Here the k function to generate a circuit or generate the columns of witness is this function next trace mask. This is to generate a new witness, and then if you want to define some constraint on this witness, you just use this function, add constraint. This function, I have some struggle with it. So this function used to create a new witness, but what in air constraint, I need a very important function is to define the transition constraint. You basically call the first row and then you call the next row, and then you want to define some constraint between these two rows. So it turns out how you create the transition constraint, you just still use this function, but you put the parameter as like this. Now I'm basically want to create, I'm able to reach the current row with this offset 0 and the next row with this offset 1. Previously, I used this function, and then I tried to do some test, but it always fails. So I thought they don't have this function to call the next row directly. And when I talk with their developers, they also give me some idea that I should use lookup. But at the end, I just find what I'm wrong. I did some very kind of stupid thing. So I make a test for this next row constraint. And the test I write is I create a witness A, let's see, and 1, 2, 3, 4. And then I want to prove A plus 1 equal to A prime. This A prime means the next row. This is my test case. Did you see what's wrong? This is okay, this is okay, this is okay, and this one. What's the next one row? It go back to the first one. Because you are in this cyclic domain, right? So what the correct test case is you should write another column, let's say last, and then I supply it as 0, 0, 0, 1, and then A plus 1 1 minus last equal to A prime. Maybe it's this way. A prime minus A minus 1. Yeah. Then I can use it to test the circuit I write. Otherwise, it's this next row is circuit I defined will always be wrong. And to solve this problem, it's really taken me a long time. I thought it's quite straightforward. It's just a stack prover. Should we have some simple API to write my circuit? But because of this thing, it took me so long time. But also one good point is because I want to solve this problem, I dig more into the algorithm. I start checking about circuit stack, and then at the end, going back to a very simple problem. Another add point is why the developer in Stwo, they told me that I should use lookup to define the rows between, define the constraint between rows. I think what he means is he thought I'm going to define some very complicated constraint between rows. Like when we use transition constraints to define rows, you always apply to every row of your trace. But if I want to define something that's several rows, like this one and this one, and then it's better to use lookup, and you do kind of lookup table things. Yeah, so this is my conclusion. Yeah, I think I will stop here.